In this video, we're going to come up with a set of circuit rules that let us analyze operational amplifiers a lot faster. And we're going to demonstrate those rules on two of the most common op-amp configurations, which are inverting and non-inverting amplifiers. In the last video, we figured out the behavior of this op-amp configuration, and we discovered that it had the nice property of buffering impedances while preserving voltages. However, we had to do this whole slide of math to figure that out. This video is about a faster way to get to the same result. Specifically, we're going to derive some rules for how op-amps affect the circuits around them. The first of these rules is pretty easy. If we approximate Rn as infinite, which is the same thing as replacing it with an open circuit, then that means that no current ever flows into the plus or minus terminal of the op-amp. Or put another way, In is always equal to 0 for an op-amp. The second rule that we're going to lean on is a little bit more involved. It says that V plus has to equal V minus if the op-amp is in negative feedback. We can show that this is true by observing that if there's any difference between V plus and V minus, and A is infinite, then V out also has to be infinite. So that means that if V plus increases at all, then V out changes a lot and drags V minus with it until the input difference is cancelled. Students are often bothered by this derivation because it's an oversimplification. Weren't you just telling us that V out is equal to A times V plus minus V minus? Wouldn't that be 0 if V plus equals V minus? The trick to resolving these complaints is to remember that A is actually finite. So in reality, there's a tiny difference between V plus and V minus, which allows for A times V plus minus V minus to be equal to V out. This argument doesn't hold water when the op-amp is in positive feedback. A little voltage difference at the input will result in a bigger value of V plus minus V minus, so the op-amp will just run away to its maximum value and rail out. This slide contains both of the previous two rules that we just engaged in, and it's labeled the most important slide. We're taking an explicit pause here to emphasize just how important these rules are. These two things and the use of them is the main thing you should take away from watching these videos. You can analyze any op-amp circuit by remembering that In equals 0 and V plus equals V minus when the op-amp is in negative feedback. Because we already know the results for a unity gain buffer, it's a really good platform for us to test these rules out and see if we get the same answer. So looking at this circuit, we can immediately tell that V plus is V sensor minus the voltage drop across R sensor. But because we know that In is equal to 0, we know that that voltage drop is 0. So V plus is equal to V sensor. We know V minus is equal to V out because they're connected with a wire. So because this is negative feedback, we can apply our rules and immediately know that V out is equal to V sensor, which agrees with our earlier analysis. This was quicker than feedback calculations, but not by a whole lot. However, this is the simplest circuit that we can imagine. We actually do even better if we analyze a more complicated circuit. So we're going to take a look at this circuit, which is called an inverting amplifier. It's not even clear how we'd use feedback rules for this circuit. Both V in and V out are hooked to V minus in some way. However, we can analyze this really effectively with circuit rules. Now, first I'm going to add some current directions to this schematic because they're important for the analysis. So first, V plus is really easy to find because it's just hooked to ground. And that means we can use our op-amp rules early on to know that V minus must also be 0. It's said to be virtually grounded by the op-amp because we enforce 0 volts on it without actually hooking it to ground. And if the voltage at V minus is 0, then the current through I has to be V in over Ri because the voltage difference across it is V in. Because no current goes into the op-amp, we know that all of the current in Ri has to wind up in Rf by KCl at the V minus node. And that's important because our last calculation is observing that V out has to be one resistor voltage drop below whatever V minus is, which is to say we can make up the V out voltage by starting at V minus and adding the drop across Rf. Because the IF current is moving from left to right, that means the positive side of the Rf resistor is on the left and V out has to be less than V minus. Next, we substitute the values in for V minus and IF, which gives us an expression for V out in terms of V in. This step bothers some students because V minus is equal to 0, but current is still coming out of the V minus node. That's only possible if V out is negative, because current flows from higher to lower voltages. So this op-amp is deliberately generating a negative voltage so that all the rules of this circuit can be met at the same time. The negative voltage allows KCl at the V minus node to be true, and helps us meet the requirement that V plus is equal to V minus. Finally, this expression cleans up rather nicely to show that the amplifier gives us a negative gain, which is why it's called an inverting amplifier. Now just to describe this in exhaustive detail, the gain is equal to minus Rf over Ri, which is negative. So a positive voltage on V in will cause V out to try to produce a negative voltage. We'll have a whole video about op-amp power supplies later, but note that this op-amp would work really poorly if the negative power supply was at ground, because V out couldn't ever reach the value it was aiming for. It would just rail out at ground. So now that you've seen an example of solving an op-amp circuit, it's time for you to give it a shot. We're going to be trying out your skills on this circuit called a non-inverting amplifier because the analysis is pretty reachable with the skills that you've just built. I'd like you to pause the video and try to figure out the gain of this amplifier configuration. And the general recipe you should use to find that gain is at the bottom of the slide. You should first find V+, then find V-, then use op-amp rules to set them equal. Okay, the process you should have followed looks like this. We know that V+ is equal to Vin because they're hooked together. V- is set by a voltage divider between Vout and ground. We can say this because there's no current being sucked into the V- node, so this is just a voltage divider. So finally we can use op-amp rules to set V+ equal to V-, and then we just need to invert the algebraic equation to get a useful result. The gain is 1 plus R1 over R2. You'll note that this value is positive for any resistors that you can pick, which is why this is called a non-inverting amplifier. One last bit of practice for you, which is a little bit of a trick question, but worth your time. Take a minute to try to find the gain of this circuit too. So the trick is that there isn't a gain for this circuit, it's just going to rail out. This is not in negative feedback, so the output should just fly to the positive or negative rail. So in summary, there are two big important op-amp analysis rules. Those are that In is equal to 0, and in negative feedback, V+ is equal to V-. The gain of an inverting amplifier is negative RF over Ri, and the gain of a non-inverting amplifier is equal to 1 plus R1 over R2. Inverting and non-inverting amplifiers are common enough that it's probably worth memorizing those gain formulas. But even though you have those formulas memorized, the main goal of this video was to familiarize you with how to analyze an op-amp and give you a little bit of practice doing so.